So, as you've seen so far, you can leverage the transpiler to drastically reduce sort of like the circuit overhead, like in terms of qubit numbers, sometimes mostly qubit gate counts and depth. And it's to no surprise that doing these sort of type of things will drastically improve the outcomes of your circuit in general. However, we can leverage the transpiler to do even further things. There are two major techniques that we can apply to sort of like improve the outcome of circuits. One is error suppression, and the other one is error mitigation. Today, I was going to focus on error suppression, which are basically techniques where we can insert additional pulses to sort of tailored to the noise, and specific to the noise of the hardware, to mitigate these noise sources or undo them before they sort of start to accumulate. Error mitigations, those are techniques where we use ensembles of circuits and averaging and post-processing to sort of like improve the observables that we try to measure. Tomorrow there's going to be a deep dive on day 3 to use these. However, today I'm going to focus on error suppression. Now in error suppression, you can go very, very deep down into the hardware and do like pulse shaping, filtering, optimal control. This is probably too much for most of you in this audience, but where you can leverage the transpiler is dynamic decoupling and twirling. We have a lot of documentation on our webpage. So, for instance, you can go to the guides and look up error mitigation, error suppression. For anyone who wants to just take a quick picture of the QR code, leads you directly to the documentations. If you want to see more information on that, you can go to the API references. There you will see what type of like dynamic decoupling sequences you can put in, what options you have available. And again, if you just want to take quickly a picture, it will immediately lead you to the API. Now, let's start with dynamic decoupling. So imagine you have a single qubit and you apply a Hadamard gate. The qubit goes from the ground state into sort of like the equatorial plane. In the equatorial plane, the qubit, if it's idling, it is very susceptible to phase noise. And by phase noise, we mean the qubit on the Bloch sphere can just like rotate around. Now, what you see here in the animation, each red arrow is basically kind of like a different rotational speed and direction as we go from shot to shot. Because it's noise, it can be random. So sometimes the qubit rotates this direction, sometimes it rotates that direction. Now, during idle times, these will accumulate, and because we have to average, it's quantum, so we take sampling, what you will end up is the black arrow. So you start out in like the perfect state, and as you average over all these instances of like random fluctuations, your black arrow will sort of like dephase and become like less pure. We can counteract that by splitting the delay time into half and inserting an echo pulse. Doing that at the right time, you basically can completely reverse or refocus any effect of these fluctuations. As you see in an animation, we started out sort of like spreading out all these red arrows. If you time it at the right point, it will just like start to refocus. All these techniques sort of like work very well for rather slow noise. And how does this now work in a circuit? Well, first, so this is a scheduled circuit. After routing and all the things that Matt and Davide have talked about, we can schedule the circuit, identify the idle times in the circuit, and insert the green pulses. So in this particular case, I picked just an XX dynamic decoupling sequence. And you'll immediately see everywhere there's an idle time, I place those in. And if you look very closely, there are a couple of idle times where I did not include them. For instance, on qubit 0 and qubit 1 and qubit 5, there's no DD pulse, or actually qubit 4 as well, at the very beginning. The reason for that is if the qubit starts in the ground state, you don't want to add more pulses, because the ground state, it cannot decay, it's the ground state, and it cannot pick up any phases. So there's no need to add these pulses. So just to quickly recap, we place these dynamic decoupling pulses into available idle times. It can reverse some of these slow noise components, and it does not give you or add any additional runtime overhead, because you just like run the same circuit. Now the point with these dynamic decoupling pulses is that they are actually an identity operation. So your circuit does not change at all. How can you do that? There are two ways. One is sort of like locally. So you just like call a path manager, the scheduling path manager. For instance, I picked here the as late as possible path manager, and then you pick the pattern dynamical decoupling path manager, where you can add like the durations of your instructions, and you can add like the dynamical decoupling sequence that you wish to use, the spreading of these sequences, and so forth. The advantage of doing it manually is you have like full control over what dynamical decoupling sequence you want to use, how you want to sort of like spread it out, because to me, kind of like as an experimentalist, dynamical decoupling is basically a filter function. So I have to sort of like set the filter function correctly to suppress certain noise components in the spectrum. So this is sort of like mostly for power users who really know what they do and really know what they want. However, there's a much easier way to do so through the Qiskit runtime. So you can add dynamic decoupling by either calling the sampler or the estimator, go to the options, and just like enable the dynamic decoupling sequence. You can add, there are a couple of various preset decoupling sequences, for instance, XP and XM. So this is sort of like the much easier way for the user to use. If you want to use dynamic coupling on top of like error mitigation, this is not only the preferred way, but basically the only way right now. If you add dynamic decoupling to your circuits and you want to do error mitigation, that will rather interfere with sort of like the layering and how we do like noise learning and like mitigation. So if you want to use it with error mitigation, you have to go through the runtime. If you go through the runtime, you have to also give it, it only accepts an ISA circuit. So just give the ISA circuit and the runtime will basically do everything for you. All right. Again, there's a lot of like documentation with a lot of examples that you can go through. It will immediately lead you to the API. The second technique that we can apply is so-called polytwirling. Polytwirling is basically a technique where we insert random poly pulses X, Y, Z before and after 2-qubit gates. And we do that in like a random fashion. So you take your circuit, you apply these poly gates before and after it, and you do that many, many times over different averaging or random instances. The reason for doing so are basically two. One, it can reduce the effect of coherent errors. So what you see here is a graphic of a single qubit Bloch sphere. The noiseless state is represented by the black arrow, so that's where basically you would end up if your quantum operation was perfect. However, sometimes our quantum operations are slightly miscalibrated, and then can have like an over-rotation. Think of it as, let's say you want to do a pi pulse, and instead of bringing you from the South Pole to the North Pole, you just slightly over-rotate. And that's represented by the blue arrow. Now, if we do twirling, what will happen is that this blue arrow will sort of like bounce back and forth around like the black one to these orange spots. And because, again, it's quantum, we have to average. So we take the average, and the average is the orange state, represented by the orange arrow. Now, if you compare those, the orange arrow, the blue, and the black one, you'll see that the orange is much, much closer to the black one than to the blue one. And so in that sense, you sort of like suppress coherent errors. Now, the thing with coherent errors is that they can accumulate quadratically. So the more of these operations you do, the further away, faster you get away from the ideal state. What twirling does, it sort of like turns that into an incoherent error, and that only accumulates linearly. So in that sense, you can really suppress coherent errors. This is not a magic bullet. So if you suffer mostly from coherent errors, this can help a lot. If you don't suffer much from coherent errors, this can sometimes actually make it worse. So it's sometimes a little bit of a trial and error experimentally, what will eventually help and what not. Now, on top of that, as I said, this is not the only reason to do polytwirling. It is, on top of that, because we want to tailor the noise. So sandwiching polys between an arbitrary noise channel, we can turn the noise channel into a poly channel. The poly channel has certain mathematical properties which really makes it much, much easier for us to learn the noise for PEA and PEC. So if you want to use error mitigation, you have to do like the polytwirling, or the polytwirling is done for you in the back end when you use the Qiskit runtime. So, how to do polytwirling in Qiskit 1.3. There's going to be a local path manager to do it just locally for yourself if you want to experiment with it and try out different things. However, if you again want to use it with error mitigation, you have to go through the runtime. And in the estimator, you just like call the options twirling, you enable it. And there are two arguments to set. One is the number of randomizations, so how many different random instances you want to call, for instance here 32, and how often you execute these random instances, here about 100 times. Now, again, as opposite to error mitigation, this does not add up into your runtime overhead. Think of it, you want to take like 10,000 shots, and you cut down those 10,000 shots into blocks of 100 shots, and each 100-shot block is just like a different implementation of polytwirling. So in total, you still just like ran 10,000 shots, and you didn't accumulate any additional overhead. Again, there's a lot of like documentation on like what options you can pick, and more explanations than I could give you here in just like a couple of minutes. With that, I'll just give it back to Elena, and she will give you a quick comparison on all the tools.